We have said several times that ENSO has a very high predictability because of a memory in the ocean, the waves that take months to travel across. And one thing to remember, as we already said again and again, is that even if the skill is zero point 0.8, in other words, you are correct 80% of the time, which is phenomenal because any forecast system that gives you 80% accuracy is considered very good. Imagine there's a stock market forecast that gets you the correct forecast 80% of the time. You can end up making a lot of money, right? But it just means 20% of the time you will be wrong. And if you bet big during those times, you could still end up losing a lot of money. Anyway, coming back to El Nino, 2024 was the recent failed forecast. It was called for a La Nina. 2023 was forecasted to be El Nino very early on in the year. We'll see in the next podcast that 2023 may have been slightly different in the way the entire El Nino event happened. What the role of the coupled processes were not as obvious as in some of the other forecasts, other El Ninos. So it's kind of interesting that models got it right anyway, and then post-mortem after the El Nino happened show that it was somewhat different. So we'll look at that here. Weekly sea surface temperature patterns in the tropical Pacific from the end of 2023 into January of 2024. Obviously, October, November, December, the El Nino was in its peak phase, and only thing to notice is that it was warm across the entire tropical Pacific. The cool pattern you typically get here wasn't there, and this is what we talked about in the RONI index, relative oceanic Nino index, because there are all these warming patterns that are not necessarily or not related to El Nino. So you can see that maybe there is some cold temperatures evolving here, but essentially by January only subsurface signature will be there, which shows that the discharge has finished and the recharge is beginning. So we'll begin to see cold waters popping up, and the front between the western Pacific warm pool and the cold tongue will be moving back. Remember, it moves eastward during El Nino. Before the El Nino peaks in December, January, February, in fact, in the fall months of that year, it will be moving back, as we saw in Joel Picot's paper on the advective reflective feedback theory for El Nino. The forecasts issued in January 2024 were already calling for a La Nina with fairly high probability. So this was DJF of 2023, which obviously was still in El Nino. January, February, March, April, and March, April, May, the El Nino began to die away. Neutral conditions were expected by April, May, June, but by May, June, July, the forecasts issued in January began to see the evolution of La Nina, and they were quite confident that there is more than a 60% probability of an El Nino emerging by August, September, October, and even the one issued in June 2024 was still very confident about La Nina going right into 2025, so 2024 into 2025, and then maybe decaying by the spring of 2025. So what were the models doing? Why were they feeling so confident? And everybody felt very confident as well because models had done such a phenomenal job of predicting the 2023 El Nino. But you can see here, if you look at the surface temperature evolution March to June, you began to see the cooling pattern and the tropical instability waves, which are very common at the end of a decaying phase of a strong La Nina. We talked about the 97-98 transition from El Nino to La Nina. So models obviously picked on these because models are, given the initial conditions, especially ocean conditions, and they begin to integrate forward. And you can see July to September, the subsurface cold anomalies were available, and models catch on to these. And this is the recharge phase. Remember, the discharge phase is where you have warm subsurface waters coming to the east. So here you are beginning to strengthen the upwelling, and cold waters are beginning to accumulate, and you warm near the surface. Cold waters come up, soak up the heat, go west, and then they begin to recharge the system. And you can see here the North American multi-model ensemble seasonal forecast in September 2024 was still calling for, observations were near neutral, but the forecasts called for a La Nina into December, January, February of 24-25, and then phasing out by the spring of 25. So obviously it was a fairly confident forecast, and obviously when such a thing happens, the papers come quickly to explain what happened. So evolution and prediction of the La Nina conditions in 24-25. This is a paper that came out more maybe in 25. Skillful El Nino Southern Oscillation prediction is one of the most important problems in climate science due to its substantial global impacts. There have been many successful examples since mid-1980s when Kane Zibiak made the first successful El Nino forecast with their simple Zibiak model. So obviously there was the forecast for 2024 where climate models significantly overestimated the likelihood. Here we examine the physical processes associated with the arrested development of La Nina conditions in 24-25. So everything looked like a La Nina, but then it was arrested because eventually it was basically neutral to very weak La Nina, and models were totally overestimating the La Nina prediction. Despite favorable subsurface cooling conditions following a strong 2023-24 El Nino, we argue that the arrested development of La Nina conditions in 24-25 resulted from weak episodic easterly wind anomalies and associated weak upwelling Kelvin wave activity. So basically during El Nino you have westerly wind bursts and downwelling Kelvin waves, and then the positive Birkness feedback. You want the other way feedbacks to go in the other way, where you have easterly wind bursts pushing the cold waters up, and divergence, upwelling, Kelvin waves, and Birkness feedback going towards stronger SST gradient across the equator, across the eastern to western Pacific in the deep tropics, and then winds getting stronger and so on. That didn't happen. Furthermore, we find that weaker Kelvin wave activity and ENSO amplitude reduction were linked to the ENSO regime shift with strengthened mean zonal seas-west temperature contrast and enhanced mean trade winds in the tropical Pacific around 2000. So this is a claim we'll look at, because there have been papers arguing that after the strong 1997-98 El Nino, there were strong La Ninas that followed for 3 years, and many people have argued that there was a regime shift, the previous one being maybe around 1976 or so. And why did it wait till 2024 to appear in to fail the forecast? That's not always easy to explain, but if you look at the conditions before and after 2000, you do see a regime shift, as we will see in a minute. So model limitations in capturing atmospheric variability and interdecadal shift contributed to the overestimated strength of the La Nina. So you have to remember that El Nino predictions are not a long integration. They are typically 3 to 6 months, 9 months, 12-month integrations after initialization. So if the mean conditions have shifted, that should have been there in the initial conditions. But if the models are not capturing the impact of that shift somehow from the initialization, then you can end up with the wrong forecast. And there are some evidences that the biases in the models do affect seasonal forecasts, and these are complicated issues. Okay, here we are looking at January 24 to April 25, and you can see there appeared to be a growth of a La Nina. Models caught on to the initial conditions and felt very confident about it, but the whole thing shifted westward, and then you actually had a mild warm conditions appear by the spring of 2025. So the La Nina, which should peak here, never really materialized, even though there were some cold conditions, and maybe some would argue that this is a Central Pacific La Nina. Remember, we saw one paper which argued that the position of the cold coldest temperatures affect the IOD differently than when you have cold SSTs closer to the coast and so on. Okay, so here we are looking at monthly mean SSTs and surface wind stresses averaged for January 1982 to December 99, the previous regime, and January 2000 to December 2024 after the regime shift of 97, 98, 99. And here are the differences. So this is argued they both look similar because you have the trade winds, you have upwelling and the cold tongue, you have warm pool, but you can see the slight difference here. It's looking warmer. Global warming is also manifested here. So whether this regime shift is part of the global warming or whether it's a natural variability as may have happened in 1976 and so on are all, not completely answered, but you can see the difference does show that there is a signature of colder regime. This is January, so these are differences of B minus A. So this is colder here, you can see it approximately, and warmer here, so you can see that here approximately as well. So that we would see as a regime shift with weaker trade winds here, as you can see with westerly anomalies, and maybe the southeasterlies are looking stronger, but the northern part maybe it's not very clear, but nonetheless definitely there is a SST signature and wind signature. So this is the observed and NMME predicted monthly Nino 3.4 SSTs with 5-month lead. We are looking at the background is the seasonal change. Let's read this here. Did I take out the we know that the upper ocean, let me make sure I read it properly. 8-month lead forecast. So you have NMME forecast here from January 24, May 24, July 24, September 24 into December of 24. And NMME definitely had a relatively strong La Nina, and there were several other models which were all saying La Nina. And this is 8-month lead. You expect 8-month lead to be worse, so 8-month lead forecasts were getting it even much colder. So you can see this one corrected a little bit and made the La Nina a bit weaker, but here it was much stronger cooling. La Nina predictions were very gung-ho. So I'm just going to jump ahead and read parts of the conclusion. We know that the upper ocean heat content is a necessary but not a sufficient condition for development of ENSO events. So that's the discharge, and that stochastic forcing is also important from both theoretical and observational perspectives. Subseasonal wind bursts are S2S wind bursts are unpredictable on seasonal to interannual timescales. They're kind of synoptic events. The models don't necessarily capture them, representing an unpredictable element of ENSO seasonal evolution. The interplay between these two elements, the predictable deterministic slowly evolving subsurface ocean heat content and the unpredictable stochastic wind forcing, determines the evolution and predictability of ENSO. We also noted that the episodic easterly wind anomalies were mostly in the eastern equatorial Pacific and also too weak to generate energetic upwelling Kelvin waves. As a result, the transport of cold subsurface water to the ocean surface was insufficient to trigger a basin-wide AFC coupling via the Birkenes feedback, inhibiting the ENSO SST anomaly growth. So the easterly anomalies also have to be more towards the dateline for Kelvin waves to come eastward and lift the thermocline, cool the sea surface temperatures, and start the Birkenes feedback. Moreover, the background or mean state changes modulate ENSO evolution and contributed to the arrest of the growth of La Nina conditions in 24-25, in particular after the regime shift of 1999-2000. Intraseasonal Kelvin wave activity along the equator in the Pacific was weaker and thermocline variability was suppressed. So you can read up the other papers that have discussed this. This would contribute to weaker ENSO amplitude variability and a weaker La Nina in 24-25. In addition, biases in most NMME models to predict the observed cooling in 2024-25 may therefore also be associated with the changes in ENSO properties and predictability across the early 21st century tropical Pacific regime shift. This is consistent with the decline of the ENSO prediction skill since 2000. So a lot of statements there. Regime shift happened, which has been documented elsewhere. ENSO variability has been argued to have changed. Regime shifts are there in the system and they can affect El Nino properties, even though it's not always clear whether more El Ninos and fewer El Ninos would also manifest in the climatologies themselves. So it's always a question of whether a regime shift happens and then El Nino properties change, or El Ninos happen and climatology looks different and then and so variability changes. So these are all kind of tricky questions that we will not answer here. I just wanted to introduce that topic since it's interesting and part of the overall discussion we have to worry about, because 2026 El Nino is looking very strong. Stochastic forcing is looking very strong. Amplitude predictions are very, very strong in all the models, and that's why there's an incredible discussion about the super El Nino coming up in the next few months. And how it will transition out is not clear. And if models don't get the stochastic forcing, are they really going to be accurate about the intensity that they are predicting? They are, claiming that the record-breaking El Nino is coming, but that only happens when you have robust westerly wind bursts feeding with the coupled system to make the El Nino grow stronger and stronger. So we have to wait and watch these things. I paused there by mistake. Okay, so let me leave it here. We'll come back and look at the 2023 ENSO separately in the next podcast.